let us begin lecture 19. So, in the last lecture at the end we started discussing nickel corrosion. I would like to say that it is whether that nickel would corrode in a particular solution, and the problem statement was, if you see the problem statement, this was the problem statement. We need to calculate theoretical tendency of nickel to corrode in deaerated water pH 8, assume that the corrosion products are H2 and NiOH whole 2, and we have the data: temperature, pressure 298 Kelvin and 1 atmosphere, solubility product of nickel hydroxide is 1.6 into 10⁻⁻16, and standard reduction potential of nickel is minus 0.25 volt. And we did these calculations, you can just go back and then see these calculations. We just wanted to see what is the concentration of nickel ion that could be present in the solution when we have this NiOH whole 2 product formation. And when we have NiOH whole 2, and this NiOH whole 2 would dissociate into Ni plus plus and OH minus ions, and we know the pH of the solution, and from the pH we can calculate what is the concentration of hydrogen ion, and then accordingly we can also calculate the concentration of OH minus ion, and that concentration will be in equilibrium as set by the solubility product of NiOH whole 2. Now, if you see that since the pH is 8, so we know the hydrogen ion concentration is 10 to the power minus 8, and since hydrogen ion concentration, the product of H plus and OH minus ion concentration is 10 to the power minus 14. So, we get OH minus concentration was OH minus ion concentration to be 10 to the power minus 6. And now, we have to look at this particular equation, which talks about the equilibrium between Ni plus plus and OH minus, and it is forming NiOH whole 2, and this NiOH whole 2 has got its own dissociation constant. So, we start from here. Now, if we see this NiOH whole 2, it can have equilibrium between Ni plus 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 2 OH minus. Now, we know that OH minus ion concentration in the solution is 10 to the power minus 6. Now, from Ksp consideration would be equal to concentration of NiOH 2OH whole 2 divided by whole 2. So, now this is a solid product which is precipitating out. So, we can consider to be 1, and then we get to Ni plus plus ion concentration, which is Ksp divided by OH ion whole 2. So, here it should be, we made a mistake. So, this 2 should be here square, because we are considering the dissociation constant. So, now if we know this, we know Ksp 1.6 into 10 to the power minus 16, and here 10 to the power minus 6 square. So, it ends up 1.6 into 10 to the power minus 4. So, I am just putting unit, concentration unit, which could be mole per centimeter cube. Now, once we have this, then initially we are assuming that nickel is corroding. So, if we have an electrode, if we see this 2 electrode, one side is hydrogen electrode and one side is nickel electrode, and when nickel is dissolving, and that is of course forming NiOH whole 2. Now, since nickel is dissolving and hydrogen is evolving, so this is H2 is evolving. So, hydrogen plus 2E equal to H2, this cathodic reaction is taking place on this particular electrode. Now, if we have a connection like this with a salt bridge, then if we connect them, the current should flow from this way to this way. So, this is positive end, this is my negative end. So, this would be my cathode and this would be my anode. So, this cell is also replicating the situation here. How it is replicating? Because in this case I have a solution with a pH 8 and in that we have a nickel piece. So, this nickel piece is forming a hub cell which is similar like this, and hydrogen evolution on the surface of the nickel piece is mimicking the hydrogen electrode on the other side. So, this is the solution and this is the solution. Here these two half electrodes have been broken. So, the entire reaction is broken into two hubs, that means two hub cell reactions, which is one side is Ni minus 2E equal to Ni plus plus, another side is this one. Now, when we have this situation, because we are assuming that the nickel is corroding, so then this side should be always positive, this side should be always negative. So, now the potential E1 which is set up on this right side should be greater than the potential on the left side. And this potential, of course, our convention is we will take reduction potential. So, E1 which is a reduction potential for H plus going to H2 and E2 reduction potential for Ni plus plus going to Ni. And in order to have nickel going into Ni plus plus, so this E1 should be E2, and if E1 is greater than E2, so the cell potential which is del E is nothing but E1 minus E2 should be positive. And if it is positive, then we see that since we know del G for the reaction is equal to nothing but minus NF del E over the cell potential, and if this is positive, so del G would be negative, and once we get del G to be negative, then we can say that the reaction is spontaneous. And since we are considering nickel is dissolving, so nickel dissolution is spontaneous, or corrosion is nickel corrosion is spontaneous. Now, then our main interest should be to find out the reduction potential on this side and the reduction potential on that side. So, let us find out. Now, we have all the ideas, all the data, because nickel ion concentration we know, which is 1.6 into 10 to the power minus 4 unit, we can consider molar unit, sorry, we can consider molar unit. So, now H plus is equal to 10 to the power minus 8. Now, let us see what potential it would get. So, E2 equal to nothing but E Ni plus plus Ni equal to E0 Ni plus plus Ni plus RT by 2F, since 2 electrons are involved for this reduction reaction, ln Ni plus plus ion concentration which is oxidant, and nickel ion concentration, nickel concentration which is the nickel metal. So, this we know minus 0.25 volt, and if it is 298 Kelvin and 1 atmosphere pressure, so then this particular quantity becomes 0.0591 we have calculated before 2, and this becomes then log, because when we take logs, the 2.303, that conversion factor from ln to log need to be multiplied with RT by F factor. So, this becomes minus 0.25 plus 0.0591 by 2 log 1.6 into 10 to the power minus 4. So, we get the value. So, the value becomes, so this becomes divided by 2 into 0.0591 equal to minus 0.25 minus 0.112 volt equal to minus 0.362 volt. So, E2 is nothing but this much. Now, we can calculate E1, which is this side, nothing but E2 equal to minus 0.0591 pH. We have done it this particular calculation before, because E0 H plus H2 equal to 0. So, E1 becomes minus 0.0591 into 8. So, this becomes minus 0.473 volt. So, del E would be equal to E1 minus E2, which is minus 0.473 minus 0.362 plus would be equal to 0.111 volt with a minus sign. There is a minus sign here. So, del G for the overall free energy change for the system, and the overall reaction is Ni plus 2H plus equal to Ni plus plus H2. This is the overall reaction. So, for that the change would be minus Nf del E, and here N is equal to 2. So, 2 into 96500 into 0.111 volt, and since there is a minus sign here, so it becomes plus into equal to plus 21384.4 joule. And remember, this is a plus sign. So, for a spontaneous process, del G should have been less than 0. As we have seen before, if we see this part, you see this is the section I am talking about. So, del G negative means spontaneous, del G positive means non-spontaneous. So, now here we are getting spontaneous and del G positive non-spontaneous, and here we are getting del G positive. So, it becomes definitely this particular process becomes non-spontaneous, means the assumption we had that the nickel would corrode, that assumption does not hold true. So, if this particular process is non-spontaneous, then the reverse process should be spontaneous. So, the nickel ion rather would get reduced. So, nickel corrosion is not feasible in the present condition. Now, let us see. So, this is the in order to find out whether the nickel would corrode or not, we are doing the calculations and all those considerations starting from here. If you see this section, this particular slide, we see that entire lot of calculations, and finally, our primary interest is to find whether del G is negative for the process or del G is positive for the process. Now, let us see if we maintain all other this particular NiOH whole 2 that is forming, and if the temperature is fixed. So, if we maintain this particular Ksp constant of NiOH whole 2 is not changing. So, it is still 1.6 into 10 to the power minus 16, and if we change pH, let us say pH becomes 3, let us see what happens. So, if pH becomes 3, then I can find out H plus ion concentration, or I can do a different route, since we have seen pH plus pOH equal to 14. So, pH is equal to 3 plus pAOH equal to 14. So, pOH equal to 14 minus 3 equal to 11. So, this can give me the concentration of pOH minus ion is equal to 10 to the power minus 11. Now, Ksp remains same. So, Ni plus plus OH minus whole 2 equal to Ksp equal to 1.6 into 10 to the power minus 16. So, that time nickel ion concentration becomes 1.6 into 10 to the power minus 16 divided by 10 to the power minus 11 is going to be 1.6 into 10 to the power minus 22 minus 16 equal to 1.6 into 10 to the power 6. This is the concentration level of nickel ion concentration in that solution. So, we can have again calculate E2, E0, which is minus 0.25 plus 0.0591 by 2 log Ni plus plus ion concentration, and this side becomes into pH is equal to 3. So, I would get 0.0591 into 3, it goes to minus 0.1773, or I can just simply say 0.1 volt, and this side becomes plus, so that concentration becomes 1.6 exponential 6, 0.183. So, this becomes minus 0.25, 0.07 volt. Now, if I try to find out del E is equal to E1 minus E2, so that becomes okay. So, we can find out del E again, and then del E becomes 0.177 minus, or which will become 0.07, which goes to 0.107. So, I still see that I get a negative del E value. So, even at a pH of 3, which is highly acidic, I could see if this data, other data hold, other data are just like the way we have considered, still we could see that the del E becomes negative. So, del E becomes negative means del G becomes positive. So, then again it becomes non-spontaneous. Non-spontaneous. So, that means we have to do a entire lot of calculations in order to see whether del G becomes negative or positive. Just like that we can have other calculations, but instead of doing this entire calculations to see whether the del G becomes negative for a particular corrosion process, we can also have another route to understand whether the system or the metal would corrode in the water system or not when it is dipped in aqueous medium with certain pH level. So, that information can be obtained from a particular diagram which is called Pourbaix diagram. See, this Pourbaix diagram is nothing but a plot between pH and potential. When a metal is exposed to aqueous medium, and whenever we are talking about a metal is exposed to aqueous medium, we take following species: oxygen, H2O, H plus ion, OH minus ion, and of course, metal and metal plus ion, or rather if we do not know what is the oxidation number, we can consider N plus ion. So, Mn plus, this M is nothing but a metal. Now, whenever we have existence of metal ion, then there could be possibility of formation of M oxygen N, this oxide can form, or M OH whole N, this hydroxide can form. So, generally these oxides or hydroxides, they have very low solubility product, and that is what they tend to settle down. So, now whenever we expose a metal in this particular system containing such ions, there could be possibility that oxygen is not present, but hydrogen ion would always be there. Now, there could be possibility of presence of oxygen, and of course, once you have a metal, there could be possibility of formation of metal ion, and if the system situation permits, we can have oxide or hydroxide. So, that time we can have the stability of different phases, for example, this phase or this phase and this phase, even this one, all those phases we can have some information from that diagram. And we are forgetting another important species, which is hydrogen, H2. So, there could be possibility of hydrogen evolution also when a metal is dipped in an aqueous medium. Just like zinc, when it is exposed to dilute HCl, where we have pH less than 7, it is acidic, then we see that hydrogen bubble forms, and of course, Ni plus ion also forms. So, this is a stability diagram between pH and potential. So, this diagram has two axes, one axis becomes this pH, another axis becomes potential, which is in volt, and this is in pH, which is a number. Now, there we can have a kind of, if you see a Pourbaix diagram of certain metal, we can see certain kind of this kind of diagram, or we can have a diagram like this. We can have a diagram like this. This is E versus pH also. So, this diagram if we see carefully, then we will see that this is metal, this is metal ion and this is metal hydroxide N or M2ON. So, this kind of boundary we can have. Now, from this diagram, without going for that calculation, detailed calculations that whether del G becomes negative or not, to understand whether the corrosion would take place or not, if we look at this diagram, then immediately we can make out that whether the metal would corrode or not. So, this is the benefit of this diagram. So, our next level of understanding would be how to construct this diagram and what are the informations we can snatch out of this diagram. And remember, this diagram plays a very important role in electrochemistry and especially in corrosion, because in corrosion sometimes you will hear that the metal is passivating, and this diagram can also tell you whether the metal would actually passivate or not. So, those information definitely we can snatch out from this diagram, and it would also enable us to find out the tendency of the metal to remain as metal or metal ion, that means corrosion, or passivating state without going for detailed calculation the way we have done for nickel. So, our next topic would be Pourbaix diagram. Let us stop here, we will continue our discussion in our next lecture. Thank you.